For nearly a century, a mysterious rock has been moving beside Earth, tracing a strange path through space, as if it were quietly following our planet. Astronomers once believed it might be fragment of the moon, but new evidence suggests its true origin could be very different. What is Kamoʻoalewa? Where did it come from, and why has it remained so close to Earth for so long? Stay with us as the science behind this unusual companion is revealed. Like the video, subscribe to the channel and join us for more journeys through the mysteries of space. The inner solar system extends from the Sun through the region occupied by Mercury, Venus, Earth and Mars, together with countless smaller bodies that travel between and around their paths. It is a compact part of the wider planetary system, yet its distances remain immense by human standards. The Sun holds almost all of the system's mass, and its gravity shapes every orbit within this bright central domain. Planets move along broad curved paths, while asteroids, dust grains, fragments of rock and streams of debris follow their own routes through the same space. Earth belongs to this ordered but restless environment, and the small object known as Kamoʻoalewa moves within it as one member of a large and varied population. The Sun dominates the region, not only through gravity but also through light, heat, radiation, and the continuous flow of charged particles called the solar wind. Close to the Sun's surfaces receive intense energy, and exposed rock experiences sharp changes in temperature. Farther outward, the warmth weakens, but sunlight still remains strong enough to illuminate planets and reveal faint objects to distant telescopes. The solar wind passes through the region in every direction, carrying magnetic fields and energetic particles. These influences slowly alter unprotected surfaces, darkening some minerals, changing their colors and breaking down exposed grains over long spans of time. Mercury follows the innermost planetary orbit. It moves through a zone of strong sunlight and severe temperature differences with no thick atmosphere to soften the changes. Venus travels farther out beneath a deep atmosphere that hides its rocky ground. Earth occupies the next broad path, surrounded by a thin layer of air, liquid oceans, and a natural satellite. Mars circles beyond Earth in a colder region with a smaller body, a thinner atmosphere, and two tiny moons. These 4 planets are called terrestrial planets because each contains a large proportion of rock and metal. Their solid nature separates them from the giant planets that lie much farther from the Sun. Between and across the planetary orbits, smaller bodies form a less obvious part of the inner solar system. Some remain mainly within the asteroid belt beyond Mars. Others move inward on elongated paths that cross or approach the orbits of planets. Many are fragments left from ancient collisions. Some may preserve material formed during the earliest stages of planetary growth. Their sizes range from large objects hundreds of kilometers across to grains too small to see without instruments. The region is therefore not empty space divided by 4 clean planetary tracks. It is a 3-dimensional field of moving matter, thinly spread but constantly changing. Earth itself travels around the Sun once during each year, moving at nearly 30 kilometers per second. Its path is not a perfect circle, although it remains close to circular compared with many asteroid orbits. The planet never returns to an absolutely fixed place because the Sun, the planets, and the wider solar system are also moving. Even so, the pattern remains stable enough for seasons, calendars, and repeated astronomical observations. Earth's gravity controls the Moon and affects nearby objects, but the Sun remains the main gravitational power over the larger region. A small body near Earth may appear closely associated with the planet while still belonging primarily to the Sun. Kamoʻoalewa is one such small body. It is far smaller than a planet and much smaller than Earth's moon. Its weak brightness makes it difficult to observe, and much of what is known comes from careful measurements of reflected sunlight. It occupies the same general solar neighborhood as Earth, but it is not an ordinary moon. Its motion is governed mainly by the Sun, with Earth adding a smaller but important influence. From a broad view, both bodies follow the same central star, each responding to gravity according to its own mass, speed, and position. The word asteroid describes a small rocky or metallic body that orbits the Sun. It does not imply a single origin, shape, or composition. Some asteroids are dense and coherent, others may be piles of fragments held together by weak gravity. Their surfaces can contain dust-broken stone, glassy material, or exposed mineral grains. Many rotate and some spin rapidly. Collisions, sunlight, and repeated planetary encounters can alter their paths. Kamoʻoalewa belongs to this general family of small solar system objects, although its present relationship with Earth gives it an unusual place within that family. The inner solar system has developed through more than 4 billion years of change. Early material circles the young Sun in a flattened disk. Dust grains collide and join, forming larger bodies. Some grow into planets while others remain small or are broken apart. Later impacts scatter fragments across wide regions. Planetary gravity removes some objects, captures others temporarily, and redirects many onto new paths. The present arrangement, therefore, carries traces of a long history rather than a perfectly settled design. Every small rock follows a path shaped by ancient formation and continuing forces. Space within this region contains very little matter compared with any atmosphere, ocean, or laboratory vacuum on Earth. Even so, the distances between planets are not completely empty. Dust reflects sunlight as a faint glow. Charged particles pass outward from the Sun. Small fragments drift along independent orbits. Comets sometimes enter from colder regions, releasing gas and dust as sunlight warms their surfaces. Against this sparse background, planets appear as dominant bodies, yet the smaller population remains scientifically important because it preserves evidence that large planets have partly erased through melting weather and geological activity. Kamoʻoalewa appears modest within this setting. It does not disturb Earth-controlled tides or shine clearly in the night sky. Its significance comes from its location, motion, and physical nature. It travels through a region shaped by the same forces that guide Earth while remaining a separate body with its own history. At the widest scale, it is neither a hidden companion in the familiar sense nor an isolated wanderer beyond the planets. It is a small sun-orbiting rock moving through Earth's part of the inner solar system where gravity creates patterns that can seem simple from a distance and become more delicate under precise observation. Across this vast region, its quiet passage remains part of the continuing movement of stone planets, sunlight, and time. Earth travels through the inner solar system along an orbital corridor shaped mainly by the gravity of the Sun. This corridor is not a solid track or a narrow tunnel. It is a moving region of space through which Earth passes while following its yearly path. The planet's orbit is elliptical, so its distance from the Sun changes over the course of each revolution. Even with this variation, Earth remains within a stable zone where sunlight temperature and orbital speed follow a repeating pattern. Small bodies can enter this region, leave it, cross it, or travel beside it for limited periods without becoming permanent companions of the planet. The motion of Earth is smooth because its speed and the Sun's gravity remain closely balanced. Gravity pulls the planet inward while its forward motion carries it onward. The result is a curved path that repeats year after year. Earth completes one orbit in a little more than 365 days, moving at an average speed of nearly 30 kilometers per second. This motion creates the basic frame within which nearby asteroids are measured. Their positions are not judged only against distant stars. Astronomers also compare their motion with Earth's changing location, allowing subtle differences in speed and direction to become visible over time. A small asteroid can remain near Earth's orbital corridor without circling Earth itself. This distinction is central to understanding Kamoʻoalewa. An ordinary moon is held primarily by a planet's gravity and follows a closed path around that planet. Kamoʻoalewa does not behave in this way. The Sun remains the dominant source of gravity acting upon it. Earth changes the details of its motion, but the asteroid continues to orbit the Sun. Its path remains close enough to Earth's path that the two bodies repeatedly return to similar positions, creating the appearance of a long association. This association depends on orbital timing. When two objects take nearly the same amount of time to circle the Sun, they can remain in the same general region for many years. Their paths may differ in shape, tilt, and distance, yet their average motion can stay synchronized. This condition is called a resonance, meaning that two orbital periods maintain a stable numerical relationship. In the case of Kamoʻoalewa and Earth, both complete a solar orbit in roughly 1 year. That shared rhythm keeps the asteroid from quickly drifting far ahead of Earth or falling far behind. The similarity does not remove all relative motion. Kamoʻoalewa moves slightly faster than Earth during some parts of its orbit and slightly slower during others. Its distance from the Sun changes and its path is tilted compared with Earth's orbital plane. As these differences combine, the asteroid appears to trace a looping route when viewed from Earth. The loop is not a physical ring around the planet. It is a pattern produced by two objects moving around the Sun at nearly the same rate. The apparent motion can seem planet-centered, even though the true gravitational arrangement remains Sun-centered. Earth's orbital corridor also includes regions where the planet's gravity becomes more important. The strength of gravity decreases with the distance, so Earth influences nearby bodies most strongly when they pass close. Farther away, the Sun's pull dominates more clearly. There is no sharp wall separating these influences. Instead, their relative importance changes gradually. A small object may be deflected during a close approach, shifted into a different orbit, or temporarily captured if its speed and direction allow. Kamoʻoalewa remains outside the ordinary domain of a stable satellite, and its path reflects a continuing balance between solar control and repeated planetary influence. The Moon occupies a very different relationship with Earth. It circles the planet at an average distance of about 384,000 kilometers and remains strongly bound to the Earth-Moon system. Kamoʻoalewa stays much farther away for most of its motion. Its distance changes greatly, and it does not complete regular planet-centered revolutions like the Moon. Because its apparent loops can surround Earth in a rotating reference frame, it may be described informally as a second moon. Scientifically, that phrase can be misleading. The asteroid is a co-orbital object, not a natural satellite in the usual sense. The orbital corridor is not entirely quiet. Venus passes inside Earth's path, Mars moves outside it, and both planets exert weak, long-term effects. Jupiter, despite its much greater distance, also influences many small bodies through its enormous mass. These forces can slowly alter orbital shape and orientation. The changes are often tiny during a single year, but become important across centuries or longer. For Kamoʻoalewa, small gravitational shifts can determine whether the asteroid remains near Earth's orbital rhythm, changes into another co-orbital state, or gradually leaves the region. Sunlight adds another gentle influence. When an asteroid absorbs solar energy and later releases it as heat, the escaping radiation produces a very small push. This process is called the Yarkovsky effect. Its strength depends on the body's size, rotation, surface material, and thermal properties. For a small object, the effect can slowly change the orbit over long periods. It does not control Kamoʻoalewa's motion from day to day, but it may contribute to the gradual drift that astronomers must consider when extending orbital calculations far into the past or future. Measurements of this corridor depend on repeated observations. Each sighting provides a position against the background sky at a known time. Many observations allow astronomers to calculate an orbit and estimate its uncertainty. The longer the observing period, the more clearly the path can be constrained. Even then, small unknowns remain because the object is faint, its surface reflects little light, and weak forces accumulate slowly. Orbital models therefore describe a range of possible future paths rather than a single, perfectly certain line. Within Earth's orbital corridor, Kamoʻoalewa remains close in rhythm but separate in identity. It shares the yearly pace of the planet without becoming part of the Earth-Moon system. Its apparent companionship grows from geometry resonance and the combined pull of the Sun and Earth. The object neither follows Earth as a moon, nor passes once and disappears like a typical visitor. It occupies a middle condition, moving beside the planet through the solar year, while preserving its own independent orbit around the Sun. The region around Earth's orbit contains more than one kind of companion. Some objects pass through only once, some return after many years, and some remain linked to Earth's motion through a shared pattern around the Sun. These bodies are called co-orbital objects when their average orbital period is close to that of Earth. The term does not mean that they occupy the same path at the same moment. It means that their motion remains connected through gravity and timing. Their orbits can differ in distance, tilt, and shape, yet the objects continue to move in a repeating relationship with the planet. Co-orbital motion appears in several forms. Each form depends on how the smaller body moves when its position is viewed relative to the planet. In an ordinary sun-centered view, both Earth and the small body travel around the Sun. In a rotating view that keeps Earth in nearly the same place, the smaller body can trace loops, broad curves, or shapes that resemble a horseshoe. These patterns are not solid paths in space. They are visual descriptions of changing positions between two bodies that orbit the Sun at almost the same rate. A quasi-satellite is one type of co-orbital object. It appears to circle a planet because its relative path forms a loop around that planet in the rotating view. The word quasi means almost or seemingly. The object looks like a satellite from this particular frame, but it is not gravitationally bound to the planet in the same way as a moon. The Sun remains the main body controlling its orbit. The planet influences the timing and shape of the motion, helping the object remain nearby without holding it in a closed planet-centered orbit. This difference separates Kamoʻoalewa from Earth's moon. The moon remains within Earth's gravitational control and repeatedly travels around the planet. Its distance changes and the Sun affects its motion, but Earth provides the main pull that keeps it as a satellite. A quasi-satellite usually stays much farther away. It can pass from one side of the planet's orbit to the other while continuing to circle the Sun. Its apparent loop may last for decades or centuries, yet the object can eventually move into another co-orbital pattern or leave the relationship entirely. Temporary capture creates another kind of nearby object. A small body can approach Earth slowly enough for the planet's gravity to hold it for a limited time. During this period, the object may complete one or more irregular revolutions around Earth before escaping. Such a body is sometimes called a temporarily captured orbiter. Unlike a quasi-satellite, it becomes genuinely bound to Earth for part of its journey. The capture is usually weak because the Sun continually disturbs the motion. A slight change in speed or direction can end the temporary bond. Some temporarily captured objects remain near Earth without completing a full revolution. These are temporarily captured flybys. They enter the region where Earth's gravity strongly affects their path, but their motion carries them away before a complete orbit forms. Their paths can be difficult to identify because they are often small, faint, and visible for only a short time. Their relationship with Earth is brief and direct, unlike the long repeating rhythm of a stable co-orbital state. Trojan objects form a different co-orbital arrangement. They remain near two regions located ahead of or behind a planet along its orbit. In the rotating view, these regions appear about 1/6 of a full circle away from the planet. The gravity of the Sun and the planet creates a stable balance that allows a small body to move around one of these areas. The body does not remain fixed at a single point. It follows a looping path around the region while keeping the same orbital period as the planet. Earth has at least a small number of known Trojan asteroids. Their detection is difficult because the most favorable regions often appear close to the Sun in the sky as seen from Earth. Bright twilight limits observations, and the objects themselves may reflect very little light. Their existence shows that Earth's co-orbital population is not limited to quasi-satellites. Different gravitational patterns can preserve a shared yearly rhythm while producing very different relative paths. Horseshoe co-orbitals travel through an even broader pattern. In the rotating view, their paths bend around both sides of the planet's orbit and avoid the immediate region near the planet. The shape resembles a horseshoe wrapped around the point where the planet appears to remain. The small body slowly approaches Earth from one direction, exchanges a small amount of orbital energy through gravity, and then reverses its relative drift. It does not turn around in space. Instead, the gravitational encounter changes its orbital period slightly, causing the body to move from trailing Earth to leading it or from leading to trailing. The exchange remains gentle when the object stays at a safe distance. A body slightly closer to the Sun moves faster and gains ground on Earth. As it approaches the planet's orbital position, Earth's gravity can lift it into a slightly wider orbit. A wider orbit takes longer to complete, so the body begins to fall behind. The opposite process occurs when it approaches from the other side. This repeating transfer produces the broad horseshoe pattern without requiring a close orbit around Earth. Some co-orbital objects shift between horseshoe and quasi-satellite states. Small changes caused by Earth, other planets, and weak non-gravitational forces can alter the pattern over time. The categories describe present motion rather than permanent identity. An asteroid is not created as a Trojan horseshoe companion or quasi-satellite in a fixed sense. It enters one of these relationships when its orbit develops the required timing and geometry. Later changes can move it into another state. Kamoʻoalewa belongs to this co-orbital population. Its significance does not come from being a second moon, since it is not one. It is part of a family of objects whose paths reveal how gravity can organize motion without permanent capture. The shared orbit creates order through resonance, while differences in distance and speed preserve separation. Within this population, apparent companionship takes several forms, each defined by motion around the Sun and by the changing geometry between a small body and Earth. Kamoʻoalewa's present motion places it in the quasi-satellite state, a special arrangement in which a small body shares Earth's yearly rhythm, while remaining in orbit around the Sun. From far above the solar system, the asteroid and Earth each follow separate paths around the central star. From a viewpoint that turns with Earth, however, Kamoʻoalewa appears to travel around the planet in a broad, uneven loop. This apparent loop creates the impression of companionship, but the motion is produced by geometry and resonance rather than by permanent capture. The asteroid completes one solar orbit in almost the same time as Earth. This near equality keeps the two bodies close in orbital longitude, meaning that they remain near the same general direction from the Sun. Kamoʻoalewa does not stay beside Earth at a fixed distance. It moves ahead during some parts of the cycle and falls behind during others. These changes occur because its orbit is slightly more elongated and more tilted than Earth's. Its speed rises when it moves closer to the Sun and falls when it moves farther away, following the same basic rule that governs every orbiting body. Seen from Earth's rotating frame, the changing speed produces a loop that closes after roughly 1 year. The loop is not circular, and Earth does not sit at its physical center. Kamoʻoalewa approaches from one side, crosses the sky through a changing angle, and then recedes toward the other side before returning. The pattern repeats because both bodies complete their solar journeys together. Each apparent circuit around Earth is therefore one expression of two linked orbits around the Sun. The distance between Earth and Kamoʻoalewa varies greatly across this motion. At its closer parts, the asteroid remains millions of kilometers away, far beyond the Moon's orbit. At its more distant parts, the separation becomes much larger. These distances prevent Earth from holding the asteroid as a normal satellite. Earth's gravity still matters, but it acts as a steady correction rather than an enclosing bond. The Sun provides the dominant pull throughout the cycle, maintaining the asteroid's independent path. The tilt of Kamoʻoalewa's orbit adds a vertical movement to the apparent loop. Earth travels close to a broad reference plane called the ecliptic, which represents the average plane of Earth's orbit around the Sun. Kamoʻoalewa's path is inclined relative to this plane. During part of each year it lies above Earth's orbital plane, and during another part it lies below. The resulting loop is therefore three-dimensional even when diagrams often flatten it onto a page. Its orbit is also more eccentric than Earth's. Eccentricity describes how much an orbit differs from a circle. Earth's orbit is only slightly eccentric, while Kamoʻoalewa's distance from the Sun changes more noticeably. When the asteroid moves inward, it travels faster than Earth. When it moves outward, it travels more slowly. These alternating differences create the forward and backward drift seen in the rotating frame. The quasi-satellite pattern emerges from this repeated exchange between faster inner motion and slower outer motion. Earth's gravity helps preserve the relationship by adjusting the asteroid's path during each cycle. The changes are small, but they prevent the relative motion from becoming a simple escape. When Kamoʻoalewa moves too far ahead, gravitational influence alters its orbital energy in a way that slows its drift. When it falls behind, the influence works in the opposite direction. The balance is dynamic rather than motionless. The asteroid continually changes position, speed, and distance while remaining within the same overall pattern. This balance does not require close approaches. Resonant motion can operate across large distances because gravity acts continuously, even when weak. The repeated timing matters more than a single strong encounter. Small effects accumulate in an organized way when two orbital periods remain linked. Kamoʻoalewa returns again and again to similar geometric positions relative to Earth, allowing the planet's influence to shape the long-term loop without drawing the asteroid into a direct orbit. The sun-centered path of Kamoʻoalewa crosses both inside and outside Earth's average distance from the Sun. During the inner part, the asteroid gains angular speed and begins to advance. During the outer part, it loses angular speed and begins to trail. These phases are smooth and gradual. No sudden turn occurs when the apparent loop changes direction. The reversal belongs only to the rotating frame where Earth is treated as almost stationary. In ordinary space, Kamoʻoalewa always continues forward around the Sun. The apparent loop also changes shape from year to year. Planetary gravity, the exact position of Earth, and small uncertainties in the measured orbit prevent perfect repetition. The broad structure remains recognizable, but each circuit differs slightly from the last. Astronomers use numerical calculations to follow these changes. A computer model begins with the best measured position and velocity, then applies the gravitational influence of the Sun, Earth, the Moon, and other planets. Repeated calculations reveal the range of paths consistent with the observations. This motion can appear puzzling in animations where the rotating frame hides the sun-centered structure. The asteroid seems to circle Earth, yet every point in the loop belongs to a solar orbit. The visual pattern changes only because the observer's frame turns with the planet. Kamoʻoalewa's faintness limits the precision of this work. It is visible only during favorable parts of its orbit, when its position, distance, and illumination allow enough reflected sunlight to reach telescopes. Observations from several years must be combined to refine the path. Each additional measurement reduces uncertainty and helps separate the asteroid's true movement from small errors in position. The quasi-satellite classification rests on this accumulated record rather than on a single image. The object's apparent companionship is therefore a result of synchronized solar motion. It neither follows Earth through space as a trailing fragment nor circles the planet as a moon. Both bodies move around the Sun, and their nearly equal periods keep their positions connected. Differences in orbital shape and tilt create the broad loop, while Earth's gravity maintains the resonant pattern. Kamoʻoalewa remains distant, independent, and continuously moving, yet its yearly path repeatedly folds around Earth's location in the rotating frame. The result is a stable-looking pattern formed from constant change, with every part of the loop produced by ordinary gravity acting across the inner solar system. Kamoʻoalewa's present relationship with Earth extends across a period that is short in planetary history, but long compared with the span of direct observation. Astronomers discover the asteroid in 2016, yet calculations indicate that its quasi-satellite motion begins many decades earlier. By reconstructing the orbit backward, researchers find that the object has remained within its current Earth-linked pattern for roughly 1 century. This conclusion does not come from photographs taken throughout that entire interval. It comes from precise modern measurements combined with the known laws of motion and carefully tested numerical models. Each observation records the asteroid's position at a specific time. Telescopes measure where its faint point of light appears against distant stars, while the observing sight, Earth's motion, and the travel time of light are taken into account. Several measurements made over one night show immediate movement across the sky. Observations separated by days, months, and years reveal the curvature of the path. From this collection, astronomers estimate 6 basic quantities describing the object's location and velocity in 3-dimensional space. Those quantities provide the starting state for calculating its motion. A numerical integration advances or reverses that state in very small steps. At every step, the calculation determines how gravity changes the asteroid's speed and direction. The Sun supplies the dominant force, while Earth, the Moon, and the other planets add smaller influences. The model repeatedly updates the position and velocity, building a continuous orbital history. Running the calculation backward does not cause time itself to reverse. It uses the reversible form of gravitational motion to determine which earlier paths are consistent with the object's measured state today. The result shows Kamoʻoalewa moving with Earth in the 1-to-1 resonance that defines its current quasi-satellite condition. Its relative position forms a broad loop around Earth in the rotating frame, and the loop remains recognizable through the reconstructed decades. Near the early 20th century, the calculated pattern changes enough to mark the approximate beginning of the present state. The exact year is not perfectly fixed because every orbital solution contains uncertainty. Researchers therefore describe the duration as about a century, rather than assigning an unquestionable date. This uncertainty begins with observation. Kamoʻoalewa is small and faint, and it is visible from Earth only during favorable intervals. Atmospheric turbulence slightly blurs its apparent position. The background star catalogue contains tiny measurement limits. The asteroid's uneven surface can shift the center of reflected light as it rotates. Each source of error is small, but backward calculations allow small differences to grow. Astronomers represent the uncertainty with a range of possible starting states rather than treating one measured orbit as exact. Computer models often create many virtual versions called clones. Each clone begins with a position and velocity that fall within the accepted measurement range. The calculation then carries all of them backward under the same gravitational laws. When most clones preserve the same general quasi-satellite behavior for a given interval, confidence in that interval increases. When their paths begin to separate widely, the earlier history becomes less certain. The century-long estimate rests on the period during which the reconstructed solutions retain a broadly shared dynamical pattern. Close planetary encounters can make orbital history especially sensitive. A small difference before an encounter can lead to a larger difference afterward because gravity bends nearby paths by slightly different amounts. Kamoʻoalewa does not need to pass extremely close to Earth for this sensitivity to matter. Repeated weak influences can accumulate across many solar revolutions. The Moon adds another moving source of gravity, and the positions of Venus, Mars, and Jupiter contribute further corrections. The reconstructed history is therefore reliable as a range of behavior, not as a perfectly traced line through every kilometer of past space. The phrase "following Earth" describes the visual and dynamical relationship, without implying that the asteroid trails directly behind the planet. Across the century, Kamoʻoalewa alternates between positions ahead of and behind Earth, while also moving inside and outside Earth's average distance from the Sun. It remains associated with the planet because the average orbital periods stay nearly equal. The asteroid's apparent loop changes gradually, yet it does not lose the defining resonance during the interval supported by the calculations. A century contains about 100 solar circuits for both Earth and Kamoʻoalewa. During every circuit, their separation changes by millions of kilometers. The asteroid never occupies one fixed station beside the planet. Its companionship consists of repeated geometry. Similar relative positions return because the difference between their average orbital rates remains small. Earth's gravity makes gentle corrections that limit the drift, while the Sun carries both bodies around the same central path. Stability at this scale means persistence of a pattern, not stillness. Human records cover only a small part of this interval. Before the discovery, images Kamoʻoalewa remains unnoticed because its reflected light is weak and its observing windows are limited. Astronomical surveys from earlier years sometimes preserve images containing objects that were not recognized at the time. When an asteroid is later discovered, researchers can search those archives for earlier appearances. Such pre-discovery observations can lengthen the measured arc and improve the orbit, although a faint object is not guaranteed to appear clearly enough for confirmation. The century estimate also depends on the forces included in the model. Gravity provides the main structure, but a small asteroid can experience a slow push from uneven thermal radiation. Sunlight warms its surface, and the later release of heat produces a minute change in motion. The strength and direction depend on rotation, shape, density, and surface properties that are not completely known. Over a single year, the effect is extremely small. Over many decades, it can shift a calculated position enough to broaden the uncertainty. Observations, therefore, indicate that Kamoʻoalewa has accompanied Earth in its present quasi-satellite pattern for approximately 100 years. The statement is a scientific reconstruction, not a direct, century-long watch. It combines measured positions, gravitational theory, thermal estimates, and many related calculations. The broad conclusion remains stronger than any exact boundary date. Through the recent human century, the asteroid and Earth repeatedly circle the Sun in near unison, separated by vast distances but joined by the quiet timing of their orbits. Its history becomes visible through mathematics long after the motion itself quietly begins. Kamoʻoalewa's quasi-satellite state is only one part of a broader co-orbital pattern. Across longer intervals, the asteroid does not remain forever within the same apparent loop around Earth. Numerical models show that its motion can shift into a horseshoe configuration where the relative path stretches far ahead of the planet, curves around the opposite side of the orbit, and then returns from behind. The change is gradual, and it develops through the same balance of solar gravity, planetary influence, and nearly equal orbital periods that governs the present relationship. In a rotating frame centered on Earth's yearly motion, a horseshoe orbit forms a broad shape that wraps around most of Earth's path. The asteroid never travels along a literal horseshoe in space. It continues to move forward around the Sun. The shape appears only after Earth's motion is removed from the view. From that perspective, the asteroid seems to approach from one side, slow its relative drift, reverse direction, and move back across the far side of the orbit. The apparent reversal is produced by a small change in orbital energy rather than by a physical turn. When Kamoʻoalewa moves slightly closer to the Sun than Earth, it travels faster because inner orbits have shorter periods. It gradually gains on the planet from behind. As the relative distance decreases, Earth's gravity gives the asteroid a gentle outward adjustment. The new path lies slightly farther from the Sun, where orbital motion is slower. Kamoʻoalewa then begins to fall behind Earth instead of gaining. In the rotating frame, this shift appears as a smooth turn at one end of the horseshoe. The opposite process occurs when the asteroid approaches from ahead. Earth's gravity draws it slightly inward, reducing the size of its solar orbit. The asteroid then moves faster and begins to pull ahead again. These exchanges are small and the object remains far from the planet during the broad horseshoe cycle. No close capture is required. Repeated gravitational influence changes the average orbital period just enough to prevent the asteroid from passing directly through Earth's position. The horseshoe pattern depends on avoidance. The asteroid and Earth share nearly the same orbit, but their timing keeps them separated. Each approach changes the asteroid's motion before the two bodies come dangerously close. The exchange resembles a slow transfer between slightly inner and slightly outer solar paths. On the inner path, Kamoʻoalewa advances. On the outer path, it retreats. The movement continues across decades or centuries, producing a large co-orbital loop that can remain stable for long intervals. Kamoʻoalewa's current quasi-satellite state occupies a smaller region within this larger dynamical landscape. In the quasi-satellite phase, its relative loop stays near Earth. In the horseshoe phase, the loop expands and avoids the planet's immediate neighborhood. The transition occurs when changes in orbital shape, orientation, and timing move the asteroid across the boundary between these patterns. The boundary is not a wall. It is a gradual shift in how the relative motion is organized. The orbit's inclination contributes to the stability of the horseshoe path. Because Kamoʻoalewa moves above and below Earth's orbital plane, it does not meet the planet's path at every apparent crossing. Vertical separation can remain large even when a flat diagram suggests a close approach. The asteroid's eccentricity also spreads its motion across different distances from the Sun. These three-dimensional differences help reduce the chance of a direct encounter while allowing Earth's gravity to continue shaping the resonance. The Moon adds small variations to the transition. Its gravity changes as it circles Earth, producing repeated but uneven corrections. Venus and Mars also contribute, especially when their positions create favorable alignments. Jupiter acts from much farther away, yet its great mass affects the long-term orientation and shape of many asteroid orbits. The combined forces slowly alter the points where Kamoʻoalewa crosses Earth's orbital plane and the directions of its closest approaches. Thermal radiation may add another slow drift. Kamoʻoalewa absorbs sunlight during its day and releases heat as its surface rotates into darkness. If the warmest region is shifted away from the point directly facing the Sun, the escaping heat produces a tiny push. The direction depends on the sense of rotation. Across long periods, this effect can move the asteroid toward or away from the exact resonant boundary, changing when a transition between quasi-satellite and horseshoe motion occurs. Long-term calculations become less certain as these small effects accumulate. Different virtual clones of the asteroid can remain together for a time and then separate into different co-orbital histories. Some may leave the quasi-satellite state earlier while others remain within it longer. Many calculations still indicate repeated movement between related resonant patterns. The details vary, but the broader conclusion remains that the present loop is temporary within a more extensive horseshoe-like evolution. The time scale of this evolution is long compared with a human life, but brief compared with the age of the solar system. A century of quasi-satellite motion can appear permanent when measured against the period of modern astronomy. In orbital dynamics, however, it is a passing phase. Small changes repeated over hundreds of revolutions can reorganize the entire relative path without destroying the one-to-one resonance. During the widest part of the horseshoe cycle, the separation can become so large that the relationship is not obvious from a simple sky image. Only a calculated orbit reveals that the distant asteroid and Earth remain synchronized with each approach, preparing the next reversal in their relative drift. A horseshoe state does not make Kamoʻoalewa less connected to Earth. It represents another form of the same shared orbital rhythm. The asteroid still completes one solar revolution in approximately 1 year, and Earth still regulates its long-term drift. What changes is the shape of the motion when viewed from the planet. The compact loop opens into a broad curve, and the object spends longer intervals far ahead or behind. Across this changing pattern, Kamoʻoalewa remains a Sun-orbiting asteroid. Earth guides its relative motion without owning it. The quasi-satellite loop and the horseshoe path are two expressions of a single gravitational relationship linked by slow exchanges of orbital energy. Over time, the asteroid moves between narrower and wider forms of companionship, always carried forward by the Sun and always adjusted by the planet whose orbit it nearly shares. Kamoʻoalewa becomes known only when modern sky surveys begin watching large areas of space with enough sensitivity, speed, and repetition to detect objects that are both small and faint. Its discovery does not begin with a bright flash or a clear image of a rocky body. It begins as a tiny point of reflected sunlight moving against the distant background of stars. The object is found in 2016 by the Pan-STARRS survey in Hawaii, where a wide-field telescope repeatedly photographs the sky and compares one exposure with another. The motion of the point reveals that it belongs to the solar system rather than to the fixed stellar background. The name Pan-STARRS refers to a survey system designed to search for changing and moving objects. Its telescope observes broad regions of sky with a sensitive digital camera. Each image contains stars, galaxies, noise, artificial traces, and sometimes an asteroid. Computer software aligns repeated images and looks for points that shift in a manner consistent with orbital motion. A candidate must then be checked carefully because faint signals can be confused with cosmic rays, image defects, or background sources. Kamoʻoalewa enters scientific records only after its movement is measured across several observations. At the time of discovery, the asteroid receives a provisional designation. Such a designation records the year and sequence of discovery before a permanent name is approved. The object is first catalogued as 2016 H03. Later, it receives the Hawaiian name Kamoʻoalewa, which refers to a celestial fragment that oscillates or moves through the sky. The name reflects the observing location and the object's shifting appearance, while the scientific identity remains tied to its measured orbit. The asteroid is difficult to see because its surface reflects only a small amount of sunlight toward Earth. Brightness depends on several factors at once. A larger body usually reflects more light than a smaller one, but surface color and texture also matter. A dark surface can make a relatively large object appear faint, while a brighter surface can make a smaller object easier to detect. Distance is equally important. Sunlight weakens as it travels outward, then weakens again after reflecting from the asteroid and returning toward a telescope. Kamoʻoalewa is also visible only during favorable parts of its orbit. Its geometry relative to the Sun and Earth changes throughout the year. At some times it lies in a direction close to the Sun in the sky where daylight or twilight overwhelms its weak glow. At other times it is farther from Earth or illuminated at an angle that presents only a small bright portion of its surface. The best observing windows occur when its separation from the Sun in the sky is large enough for darkness, and when its distance and illumination combine to produce measurable light. Even during favorable periods, the asteroid remains unresolved in ordinary telescope images. It does not appear as a disk with visible edges. The image is a point spread across several camera pixels by the telescope's optics and Earth's atmosphere. Astronomers, therefore, cannot measure its diameter directly from a sharp picture. They infer size from brightness, estimated reflectivity, thermal emission, and the way light changes as the object rotates. Every estimate carries uncertainty because one unknown property can affect another. Atmospheric conditions place further limits on observation. Air moves in layers with different temperatures and densities, bending incoming light by slightly changing amounts. This turbulence makes stars shimmer and causes faint points to blur. Thin clouds, moisture, moonlight, and dust can reduce contrast. Observatories at high elevations help by placing telescopes above part of the atmosphere, but no ground-based site removes the problem completely. Careful calibration is needed to distinguish the asteroid's real signal from changes introduced by the air and the instrument. Tracking a faint moving object requires precise timing. The asteroid shifts position while the camera collects light. If an exposure is too long, the object can form a short streak rather than a compact point. A streak spreads the available light over more pixels and can become harder to detect. If an exposure is too short, too few photons arrive to create a reliable signal. Observers balance these effects by selecting exposure times that preserve enough brightness while limiting motion blur. After discovery, follow-up observations become essential. A few positions define only a rough path, and many different orbits can fit a short arc. Telescopes at other locations observe the candidate over following nights and weeks. Each new measurement narrows the range of possible paths. International reporting systems collect the data, compare independent observations, and update the calculated orbit. Without this follow-up, a faint asteroid can become lost because the predicted search area grows too large before the next observing opportunity. Kamoʻoalewa's near-Earth motion creates additional difficulty. Its apparent speed and direction change as Earth moves, and its tilted orbit carries it across different parts of the sky. The asteroid may be observable for a limited season and then disappear into an unfavorable solar direction. Astronomers must recover it during later windows to extend the observation arc. Successful recovery confirms that the calculated orbit predicts the real object and improves confidence in its co-orbital classification. Brightness measurements also reveal rotation. An irregular asteroid reflects different amounts of light as different sides turn toward Earth. Repeated observations produce a light curve, a record of brightness changing with time. A regular pattern can show the rotation period, although interpretation is complicated by shape surface markings and changing viewing angle. For Kamoʻoalewa, these variations indicate a rapid spin and an uneven body rather than a perfect sphere. The discovery of Kamoʻoalewa therefore rests on accumulated faint signals. No single image reveals its orbit shape or relationship with Earth. Repeated exposures establish motion, follow-up measurements constrain the path, and brightness changes offer clues about rotation. The asteroid emerges gradually from the background through careful comparison rather than direct visual detail. Its existence is clear because the same moving point returns in calculated positions, carrying a weak reflection of sunlight across the dark field of distant stars. Through this process, a body too dim for unaided sight becomes measurable, predictable, and scientifically distinct, even while its actual surface remains hidden within a point of light crossing the carefully recorded sky over many nights. Kamoʻoalewa's path is shaped by forces of different strengths. The Sun provides the dominant gravity holding the asteroid in its yearly orbit. Earth adds a smaller timed influence as the asteroid repeatedly returns to the planet's orbital neighborhood. The Moon and other planets contribute weaker changes, while sunlight produces a minute thermal push accumulating over long periods. Together, they create an orbit stable over short intervals but slowly changing across decades and centuries. Every body with mass attracts every other body, and the strength of that attraction depends on mass and distance. The Sun contains most of the solar system's mass, so its pull controls Kamoʻoalewa's motion. The asteroid falls toward the Sun while moving forward fast enough to miss it. This balance produces a curved solar orbit. Earth does not replace the Sun as the central body. Instead, Earth adjusts the asteroid's speed and direction whenever their positions create a favorable gravitational geometry. These adjustments are called perturbations, meaning small changes added to an otherwise simpler orbit. A perturbation may alter the shape of the path, tilt its plane, rotate its orientation, or change the time needed to complete one revolution. A single weak encounter often produces only a tiny effect. Repeated encounters can produce a larger result because the changes accumulate. Kamoʻoalewa's one-to-one resonance with Earth makes this repetition especially important. Similar arrangements return again and again, allowing Earth's gravity to organize the asteroid's relative motion. The distance of each approach matters. Gravity becomes stronger at shorter range, so a closer passage causes a larger deflection. Kamoʻoalewa normally remains far beyond the Moon, but even distant encounters influence its orbital energy. The direction of the encounter also matters. If Earth pulls the asteroid forward along its path, the asteroid gains orbital energy and can move into a slightly wider solar orbit. If the pull acts backward, it loses energy and can move inward. These exchanges are small, yet they help maintain or alter the co-orbital pattern. The Moon complicates the local gravitational field. It circles Earth, while both bodies travel around the Sun, so its influence changes from one encounter to another. The Moon's mass is much smaller than Earth's, but its position can slightly increase or decrease the total deflection. Accurate models, therefore, treat Earth and the Moon as separate bodies. Their combined motion adds subtle variations to Kamoʻoalewa's path, especially when the asteroid passes through regions where the geometry of the three bodies becomes important. Venus and Mars also affect the orbit. Their gravity is weaker at Kamoʻoalewa's usual distance, but they act over long spans of time. Venus can alter the inner parts of the asteroid's path, while Mars influences the outer parts. Jupiter remains much farther away, yet its great mass allows it to create slow changes in the orientation and eccentricity of many small body orbits. No single distant planet determines Kamoʻoalewa's state, but the combined planetary system gradually reshapes the path. Gravity is not the only influence. Sunlight carries momentum, and photons produce a tiny pressure when they strike a surface. Direct radiation pressure matters most for very small particles, but it can still create a slight effect on an asteroid. More important for a body like Kamoʻoalewa is the delayed release of absorbed solar heat. The asteroid warms during daylight and cools as its surface rotates into darkness. Thermal energy leaves as infrared radiation, and the escaping radiation produces a small recoil. This process is called the Yarkovsky effect. It acts like a gentle, continuous push whose direction depends on rotation. If the asteroid spins in the same general direction as its orbit, the warmest region is usually carried into the afternoon side before releasing most of its heat. The recoil can slowly increase the size of the orbit. If the spin is opposite, the effect can slowly reduce the orbit. The actual response depends on shape, surface roughness, density, thermal conductivity, and the orientation of the spin axis. Kamoʻoalewa rotates rapidly, which influences how heat moves through its surface. A dusty layer responds differently from exposed solid rock. Fine grains can insulate deeper material, allowing strong temperature differences between day and night. Solid stone can conduct heat inward and release it later. Dark material absorbs more sunlight, while brighter material reflects more. Because these properties are not fully known, the exact thermal force remains uncertain. Observations can constrain it only after the orbit has been measured across a sufficiently long interval. The Yarkovsky effect is extremely weak during one revolution. It cannot be felt as a sudden change, and it does not explain the broad orbit by itself. Across thousands of revolutions, however, the accumulated shift can become large enough to change encounter timing. A difference of only a small distance in 1 year can become a much larger positional difference after many decades. This makes thermal drift important when researchers calculate the asteroid's past or future co-orbital state. Rotation can also change slowly through uneven thermal emission. This related process is called the YORP effect, named from the surnames of researchers connected with its development. Sunlight reflected or released from an irregular shape does not always balance perfectly. The resulting torque can speed up rotation, slow it down, or shift the spin axis. Changes in spin then alter the Yarkovsky force, linking the asteroid's rotation and orbital evolution. The effect remains difficult to measure for such a faint object. Researchers model these influences by creating many possible versions of the asteroid. Each version receives different orbital values and physical assumptions within the allowed range. Some models include only gravity, while others add thermal forces with different strengths and directions. The resulting paths remain close for a time, then separate gradually. Where most paths agree, the motion is relatively secure. Where they diverge, the long-term history remains uncertain. Observations indicate that gravity preserves Kamoʻoalewa's present relationship with Earth, while weak forces slowly modify its details. The Sun carries it around the solar system. Earth regulates its shared rhythm, and other bodies add smaller corrections. Heat, escaping from the surface, provides an almost imperceptible drift. None of these influences acts alone. The measured orbit is the combined result of constant solar attraction. Repeated planetary perturbations, rotating, surface temperatures and time, all working quietly on a small body moving through Earth's orbital region. Kamoʻoalewa remains too small and too distant for ordinary telescopes to reveal a clear outline. Its body appears as a moving point of light, so astronomers estimate its size, shape, and rotation indirectly. These estimates begin with brightness. A larger object generally reflects more sunlight than a smaller one, but the amount also depends on how reflective the surface is. Because reflectivity is uncertain, the diameter cannot be stated as one exact value. Observations indicate that Kamoʻoalewa is probably only several tens of meters across, placing it among the smaller known near-Earth asteroids. An asteroid of this scale is tiny compared with the Moon, yet it remains large enough for gravity to hold its material together. Its own gravity is extremely weak. A person standing on such a body, if that were physically possible, would weigh only a small fraction of ordinary weight on Earth. Loose grains could escape easily after a disturbance, especially if the surface rotates quickly. The object's small mass also allows sunlight and thermal radiation to influence its orbit more strongly than they would affect a large planetary body. Brightness estimates depend on a property called albedo, which describes the fraction of incoming light reflected by a surface. A dark, carbon-rich asteroid can absorb most sunlight and appear faint even if it is relatively large. A brighter, silicate surface can reflect more light and appear similar in brightness while being smaller. Without a direct measurement of albedo size, calculations produce a range rather than a single diameter. Thermal observations can reduce this uncertainty because heat emission depends differently on size and reflectivity, but Kamoʻoalewa's faintness makes such measurements difficult. The changing brightness of the asteroid reveals more than its average size. As Kamoʻoalewa rotates, different parts of its surface face Earth and the Sun. If the body were a perfect sphere with uniform color, the brightness would remain nearly constant under the same geometry. Instead, repeated observations show a regular variation. This pattern forms a light curve, a record of brightness measured across time. The rise and fall indicate that the visible cross-section or surface reflectivity changes as the asteroid spins. The light curve suggests that Kamoʻoalewa completes one rotation in roughly half an hour. This is a rapid spin for a small asteroid. Although very small, rocky bodies can rotate faster than larger rubble piles. The measured period represents the time required for the brightness pattern to repeat. Astronomers must consider whether one full rotation produces one brightness maximum or two. An elongated body commonly presents a broadside twice during each rotation, creating two similar peaks. Careful analysis is needed to identify the most likely rotational period. Rapid rotation places stress on the asteroid. Material near the equator experiences an outward effect caused by the spinning motion. On a large body, gravity can resist this effect. On a small asteroid, gravity is weak, so the internal strength of rock becomes important. If Kamoʻoalewa where a loosely assembled pile of fragments with almost no cohesion, a sufficiently rapid spin could cause grains or larger pieces to escape. Its survival, therefore, suggests that the body has some structural strength, although it may still contain cracks, pores, and separate blocks. The term monolithic is sometimes used for an asteroid that behaves mainly as one coherent piece of rock. This does not require it to be flawless or completely solid. A monolithic body can contain fractures and damaged zones while remaining mechanically connected. A rubble pile asteroid, by contrast, consists of many pieces held together mostly by gravity and weak contact forces. Kamoʻoalewa's small size and rapid rotation are more consistent with a body that has meaningful cohesion, but current observations do not reveal its internal arrangement directly. Its shape is also uncertain. The brightness variation indicates that the body is not perfectly spherical, yet several forms could produce the same light curve. It may be elongated, angular, flattened, or covered with regions of different brightness. An elongated body presents a changing area as it rotates, while a mottled surface can vary in brightness even with a rounder shape. Observations made from different viewing angles help separate these possibilities, but the available windows are limited and the object remains faint. Small asteroids commonly develop irregular forms through collisions. An impact can break a larger body and release fragments with sharp, uneven shapes. Later impacts can chip their surfaces open cracks and create loose debris. Kamoʻoalewa may be a fragment from such an event, although its source remains uncertain. Its present form reflects both the violence of its creation and the gradual alteration that follows. With no atmosphere, rain, or flowing water, sharp structures can survive while micrometeorite impacts slowly crush exposed material into finer grains. Rotation may also affect the surface distribution. Loose particles tend to move toward regions where the combined gravitational and rotational forces allow them to settle. On a rapidly spinning object, slopes can fail and grains can migrate towards the equator. If the body has enough cohesion, steep faces may remain stable. If cohesion is weak, material can shift during small impacts or thermal cracking. These processes can change the light curve over time, although no clear, rapid surface change has been established for Kamoʻoalewa. The spin axis, the imaginary line around which the asteroid rotates, adds another unknown. Its orientation controls how sunlight reaches different regions and how heat is released into space. It also affects the direction of the Yarkovsky drift. A spin axis tilted toward the orbital plane produces a different thermal pattern from one standing nearly upright. Light curves collected across several observing seasons can constrain the orientation, but they may not provide a unique answer. Shape, rotation, and size therefore remain connected. Brightness supplies the first measurement, but it must be interpreted through assumptions about reflectivity and geometry. The rapid light variation indicates a small, irregular body turning many times during a single day on Earth. Its structural strength is sufficient to preserve the body against rotational disruption, yet its internal composition remains hidden. Kamoʻoalewa is known not as a resolved world with visible cliffs and craters, but as a compact, spinning source of faint light whose repeated changes reveal the outline of a small and uneven rock moving beside Earth under the distant glare of the sun. Kamoʻoalewa's outer surface receives sunlight without the protection of an atmosphere. During each rotation, one region turns toward the sun, warms, and then moves into darkness. Because the asteroid spins rapidly, this cycle repeats often during one day. The changing temperature allows astronomers to study more than visible brightness. Warm rock releases infrared radiation, a form of light, with wavelengths longer than those seen by human eyes. Measuring this thermal glow can help constrain the asteroid's size, reflectivity, surface roughness, and ability to conduct heat. Visible brightness alone cannot determine size because a small bright object can resemble a larger dark one. Thermal emission provides a second measurement. A larger surface generally releases more heat than a smaller surface under similar illumination. A dark object absorbs more sunlight and becomes warmer, while a bright object reflects more and usually remains cooler. By combining visible and infrared observations, researchers can compare reflected energy with emitted heat. This method can reduce the range of possible diameters and surface reflectivities, although weak signals and uncertain geometry limit precision. The temperature of an airless body is uneven. The sunlit side can become much warmer than the dark side, and the hottest point does not always lie directly beneath the sun. Heat takes time to move through rock and dust. As the surface rotates, the warmest region may shift toward the afternoon side, where sunlight has already begun to weaken. The amount of this delay depends on thermal inertia, which describes how strongly a material resists changes in temperature. Dense rock usually has higher thermal inertia than loose, fine dust. A surface with low thermal inertia heats quickly in sunlight and cools quickly in darkness. Fine powder and porous soil often behave this way because empty spaces between grains slow the movement of heat. A surface with high thermal inertia changes temperature more slowly. Solid stone-dense blocks and compact material can store heat and release it after sunset. By observing how thermal radiation changes during rotation, astronomers can estimate which general behavior fits the asteroid. For Kamoʻoalewa, measurements remain limited, so several combinations of rock dust and porosity may still match the available data. Surface roughness also changes the thermal signal. A smooth sphere receives sunlight in a simple pattern, but a real asteroid may contain pits, ridges, fractures, and angular faces. Slopes point toward or away from the sun at different times, creating local hot and cold regions. Small cavities can trap radiation between their walls, causing repeated absorption and warming. Rough surfaces can also direct more infrared energy toward an observer at certain angles. This concentration is sometimes called thermal beaming, although no narrow beam is physically produced. Thermal models represent these effects with simplified shapes and adjustable properties. One model may treat the asteroid as a sphere with a uniform surface. Another may include an elongated shape, a roughness factor, and a selected value for thermal inertia. Researchers calculate the temperature of each surface region as sunlight changes and then predict the infrared brightness seen from Earth. The predictions are compared with observations. Models that fail to match the data are rejected, while those that fit define a range of plausible physical conditions. Kamoʻoalewa's rapid rotation affects the temperature pattern strongly. Each surface region spends only a short time in direct sunlight before turning away. Heat may not penetrate deeply during such a brief interval. The daily thermal wave, meaning the layer influenced by repeated heating and cooling, may reach only a small depth below the surface. Beneath that layer, temperatures change more slowly. The exact depth depends on conductivity, density, heat capacity, and rotation period. Loose grains create a shallow response, while coherent rock can carry warmth farther inward. Repeated heating and cooling can alter the surface over long periods. Rock expands when warmed and contracts when cooled. On an airless asteroid, large temperature changes can create stress along mineral boundaries and existing cracks. This process, called thermal fatigue, can gradually break exposed stone into smaller pieces. Tiny impacts add further damage, crushing grains and opening fractures. The resulting surface may contain a mixture of solid blocks, sharp fragments, and fine material rather than one uniform layer. The amount of loose material is uncertain because Kamoʻoalewa's gravity is weak and its rotation is fast. Fine grains produced by impacts may escape if they receive enough speed. Other grains may remain trapped in low areas or cling through weak electrical and contact forces. Rapid rotation reduces effective gravity near the equator, making movement and loss of material easier there. A coherent rocky body can still carry patches of dust, but broad, deep deposits may be difficult to preserve on steep or rapidly moving surfaces. Reflectivity can vary from place to place. Freshly exposed mineral surfaces may appear brighter or display stronger spectral features than older regions altered by space weathering. Space weathering is the gradual change caused by radiation, solar wind, and tiny impacts. It can darken some materials, redden their reflected light, and weaken diagnostic mineral bands. If Kamoʻoalewa has areas of different age or texture, its brightness and color may change slightly as it rotates. Current observations do not resolve such regions directly, so any surface variation must be inferred from repeated light measurements. The surface also controls the slow thermal force that changes the orbit. Heat released from the afternoon side produces a tiny recoil. Roughness, conductivity, spin direction, and thermal inertia determine the size and direction of this effect. Better thermal measurements would therefore improve both physical models and long-term orbital calculations. The outer layer is not only a record of impacts and radiation, it also participates in the asteroid's motion through space. Observations indicate that Kamoʻoalewa is a small, rapidly rotating body with a surface that absorbs, stores, and releases solar energy in a measurable pattern. Its exact diameter, reflectivity, roughness, and thermal inertia remain uncertain because the infrared signal is faint and observing opportunities are limited. Still, heat offers information that visible light alone cannot provide. Across each rotation, sunlight enters the uppermost grains, moves through shallow material, and returns to space as infrared radiation. That quiet exchange reveals the physical character of a surface too distant to image clearly, connecting temperature, texture size, and orbital drift within the thin outer skin of the asteroid. Kamoʻoalewa's surface remains invisible as a detailed landscape, yet the sunlight reflected from it carries information about the materials exposed there. Astronomers study this light with spectroscopy, a method that separates radiation into a sequence of wavelengths. A spectrum resembles a carefully measured distribution of brightness across color, extending beyond the narrow range visible to human eyes. Minerals do not reflect every wavelength equally. Their atoms and crystal structures absorb some portions of the incoming light and return others more strongly. These patterns allow a distant point of light to reveal broad clues about composition without showing individual rocks or grains. The process begins when sunlight reaches the asteroid. Solar light contains many wavelengths, and its original pattern is already well measured. Some of that energy enters surface minerals, some becomes heat, and some scatters back into space. A small fraction travels toward Earth and enters a telescope. Instruments divide the collected light with prisms, gratings, filters, or related optical systems. Detectors then record the relative brightness in each wavelength interval. Researchers correct the measurements for Earth's atmosphere, the telescope, the detector, and the known spectrum of the Sun. Kamoʻoalewa is faint, so spectroscopy demands more light than ordinary position measurements. A telescope may detect the asteroid as a moving point during a short exposure, but a useful spectrum requires enough photons across many wavelength channels. Longer observations improve the signal, yet the asteroid moves against the stars and changes brightness as it rotates. The telescope must follow its predicted motion, and the data must be combined without smearing the spectral pattern. Background stars, airglow, thermal radiation, and detector noise must also be removed. Ground-based observations first trace Kamoʻoalewa's reflected light from visible wavelengths into the near-infrared. Visible light covers the colors detected by human vision, while near-infrared light lies just beyond red. Together, these wavelengths contain features produced by common rock-forming minerals. The measured spectrum rises toward longer wavelengths, producing what astronomers describe as a red spectral slope. This does not mean that the asteroid appears bright red to an observer. It means that its surface reflects proportionally more long-wavelength light than short-wavelength light across the measured range. A slope can be shaped by several properties. Mineral composition affects the basic reflectance pattern. Grain size changes how deeply light enters the surface before scattering back. Roughness creates shadows and multiple reflections. Space weathering alters exposed grains through solar wind radiation and tiny impacts. Observing geometry also matters because brightness and color can shift with the angles between the Sun, asteroid, and telescope. A red slope, therefore, provides evidence, but it does not identify one material by itself. Broad absorption bands offer more specific clues. Silicate minerals contain silicon and oxygen combined with elements such as iron, magnesium, and calcium. Their crystal structures absorb near-infrared light in recognizable regions. Kamoʻoalewa's spectrum contains a weak feature near a wavelength of about 1 micrometer. The position and shape of this feature indicate that silicate material is present on the surface. The band is shallow, which makes its exact center and width difficult to measure. Noise rotational brightness changes and the steep spectral slope can affect the result. Earlier measurements extend across wavelengths from roughly 4/10 to more than 2 micrometers. They show an unusually red continuum and a subdued silicate feature. Comparisons with spectral libraries find similarities to heavily altered rocky materials, including some samples and soils from the Moon. These comparisons use normalized curves rather than direct images. Researchers adjust spectra to a common brightness level and examine slope band location, band depth, and overall shape. A close match means that two surfaces reflect light similarly under measured conditions, not that they must share an identical origin. Later observations from space provide a different view because they avoid absorption and turbulence in Earth's atmosphere. Measurements obtained with the James Webb Space Telescope cover near-infrared wavelengths with high sensitivity. They indicate a more neutral slope from about 1 to 2.5 micrometers than the earlier ground-based data suggest. New ground-based measurements made with comparable methods also support the less extreme infrared color. The faint absorption near 9/10 of 1 micrometer remains present, while a clear absorption near 2 micrometers is not detected. These differences do not make spectroscopy unreliable. They show how difficult the target is and how strongly results depend on calibration, observing conditions, rotational phase, and wavelength coverage. Kamoʻoalewa turns many times during a long observing sequence. If its surface is not uniform, spectra collected at different times may sample different mixtures of terrain. Even with a uniform surface, changing brightness can complicate the joining of separate wavelength ranges. Independent observations help reveal which features repeat and which may arise from measurement limits. Astronomers compare the newer spectrum with several asteroid classes. S-type bodies are dominated by stony silicates and commonly display absorption near 1 and 2 micrometers. V-type asteroids often show stronger bands associated with basaltic minerals. E-type bodies have bright surfaces and may contain enstatite-rich material, a magnesium silicate with little iron. Kamoʻoalewa's weak band, relatively neutral infrared color, and apparently high reflectivity can resemble parts of more than one group. Spectral classification, therefore, remains dependent on the full quality of the data and on physical surface effects. Laboratory spectra provide essential context. Scientists illuminate meteorites, lunar samples, crushed minerals, and artificial mixtures under controlled conditions. They vary grain size, viewing angle, temperature, and exposure to simulated space weathering. These experiments show that the same starting rock can produce different spectra after crushing, melting, darkening, or coating with tiny metallic particles. They also show that unrelated materials can sometimes develop similar broad curves. Matching Kamoʻoalewa requires attention to both mineral absorption and the processes that modify reflected light. The reflected light spectrum establishes a firm general result. Kamoʻoalewa has a rocky surface containing silicate minerals. Beyond that level, interpretation remains open because the diagnostic bands are weak and the continuum has changed between observing sets. The asteroid's light carries a real mineral signature, but distance, rapid rotation, surface alteration, and limited photons soften its details. Spectroscopy narrows the possible materials by measuring how the surface treats each wavelength, turning a faint, moving point into a restrained record of crystal structure, grain texture, and exposure to space. Across the long silence surrounding its small body, beneath the changing color of Kamoʻoalewa's surface lies a mixture of silicate minerals shaped by long exposure to open space. Silicates are minerals built mainly from silicon and oxygen, often combined with magnesium, iron, calcium, or other elements. They form much of the rocky material in the inner solar system, including large parts of Earth, the Moon, and many asteroids. The spectrum of Kamoʻoalewa indicates that such minerals are present, but the weakness of the absorption bands shows that the outermost grains no longer reflect light like fresh, unaltered rock. Freshly broken stone often displays stronger mineral features than an old exposed surface. When a collision opens a new fracture, clean crystal faces can reflect and absorb sunlight in a relatively clear pattern. Over time, solar wind, energetic radiation, and micrometeorite impacts change those grains. This gradual alteration is called space weathering. It does not resemble weather on Earth because there is no rain, air, frost, or flowing water. Instead, the process develops through particles, radiation, heat, and repeated impacts acting directly on an airless surface. The solar wind is a stream of charged particles flowing outward from the sun. Most are protons and electrons with smaller amounts of heavier ions. When these particles strike exposed minerals, they can enter the uppermost atomic layers, displace atoms, and damage crystal structures. Some remain implanted within the grains, others release secondary particles or contribute to chemical changes. The affected depth is extremely small, yet reflected light interacts strongly with this thin outer layer, allowing microscopic damage to change the appearance of the entire surface. Energetic particles from beyond the solar system also reach Kamoʻoalewa. These cosmic rays travel at high speeds and can penetrate more deeply than ordinary solar wind particles. Their collisions break atomic bonds, create defects, and produce new isotopes within exposed material. The changes accumulate slowly. A single particle has almost no visible effect, but countless impacts across thousands or millions of years leave a measurable record. Laboratory analysis of a returned sample could use some of these products to estimate how long grains remain exposed near the surface. Tiny natural projectiles strike the asteroid at high speed. Many are no larger than dust grains, yet their velocity gives them enough energy to melt or vaporize small patches of rock. Each impact creates a microscopic crater, sends fragments outward, and produces a brief cloud of hot material. Some of this material settles back onto the surface if its speed remains below the asteroid's weak escape velocity. Much of it may leave permanently. The balance depends on impact direction, local slope rotation, and the strength of the target. Impact heating can create small glassy coatings. Melted material cools quickly in the vacuum of space, forming irregular glass that surrounds or joins mineral grains. Vaporized atoms can condense as extremely small particles, including tiny grains of metallic iron when iron-bearing silicates are present. On many rocky bodies, these particles darken the surface, redden the reflected spectrum, and weaken absorption bands. The exact result depends on composition. Lunar soils show one familiar form of this process, but asteroid surfaces do not always respond in exactly the same way. Kamoʻoalewa's unusually weak spectral feature may therefore reflect alteration rather than an absence of silicate minerals. A fresh interior could contain stronger mineral bands than the exposed surface suggests. Space-weathered coatings can mask the original signal by changing how light scatters through each grain. Fine particles increase the number of internal reflections, while dark inclusions absorb light before it returns to space. The observed spectrum becomes a combined record of composition, grain size maturity, and surface history. The rate of weathering depends on distance from the Sun. Kamoʻoalewa remains near Earth's orbit, where solar wind and sunlight are stronger than in the outer asteroid belt. Its surface may therefore change relatively quickly compared with material farther from the Sun. However, the asteroid's small size and rapid rotation complicate the process. Impacts can remove old grains, expose fresh rock, and scatter debris away. Thermal cracking can continually produce new surfaces. Weathering and renewal occur together, so the outer layer may contain grains of many different exposure ages. Daily heating also affects mineral boundaries. As sunlight moves across the rotating body, different minerals expand and contract by slightly different amounts. Repeated cycles create stress where crystals meet. Existing cracks slowly lengthen and small flakes can detach from exposed faces. On Earth, air and water often enter these cracks and accelerate breakdown. On Kamoʻoalewa, the process remains dry, but the temperature cycle repeats rapidly because the asteroid rotates in about half an hour. Many small cycles can accumulate into significant damage over long intervals. The surface layer may be only a loose scattering of particles in some places and solid fractured rock in others. Kamoʻalewa's gravity is too weak to hold a deep blanket of debris easily, especially near regions where rotation reduces the effective downward pull. Fine material can move after impacts or electrostatic charging. Sunlight can cause exposed grains to gain or lose electrons, creating small electrical forces. These forces are weak, but on a tiny body they may help shift dust across short distances or lift the smallest particles from the surface. Mineral identification remains difficult because weathering can make different materials resemble one another. Enstatite, pyroxene, olivine, and mixtures of these minerals produce absorption features that change with iron content, grain size, and alteration. A shallow band, near 1 micrometer, can arise from several combinations. The absence of a strong band near 2 micrometers narrows the possibilities, but it does not provide a single answer. Observations indicate a silicate-rich surface, while the proportions and exact mineral chemistry remain uncertain. The outer grains of Kamoʻoalewa therefore form a thin archive of exposure. Solar particles damage crystal lattices, cosmic rays leave deeper traces, microscopic impacts melt and vaporize small regions, and repeated heating opens fractures. These processes soften the original mineral signature without erasing it completely. Beneath the altered coating, the rock may preserve a clearer record of formation, but remote light reaches mainly the weathered skin. What telescopes measure is not only the material itself, but also the long work of space upon that material written across grains too very small to resolve and carried outward in a faint weathered pattern of reflected sunlight. The lunar fragment hypothesis begins with a simple physical possibility. A large impact strikes the moon, breaks bedrock, and accelerates fragments away from the crater. Most fragments rise and return to the lunar surface. Some travel far enough to circle the moon or enter complicated paths around Earth. A much smaller fraction escapes the combined Earth and Moon region and begins orbiting the Sun. Under rare launch conditions, one escaped fragment can settle into an orbit close to Earth's, where repeated gravitational encounters gradually shape a co-orbital relationship like the one followed by Kamoʻoalewa. The Moon has no thick atmosphere to slow incoming asteroids. Projectiles reach the surface at many kilometers per second, releasing energy into a small region of crust. Rock is compressed, heated, fractured, melted, and thrown outward. Material near the impact point can leave at very high speed, while deeper or more distant material moves more slowly. The resulting ejecta form a wide curtain of particles and blocks. Their directions and speeds depend on the impact angle, projectile size, target strength, crater shape, and location on the rotating moon. To escape the moon permanently, a fragment leaving the surface requires a speed of roughly 2.4 kilometers per second, although Earth's nearby gravity complicates the exact path. A fragment moving only slightly faster than this threshold can leave the moon with a relatively low speed compared with Earth. That low residual speed is important. Material departing too quickly often enters a solar orbit very different from Earth's. Material escaping gently can remain near Earth's distance from the Sun, creating the starting conditions required for later co-orbital motion. Numerical simulations test this process by releasing thousands or millions of virtual fragments from different lunar locations. Each particle receives a selected direction and launch speed. The model then follows the gravity of the Moon, Earth, Sun, and planets. Most simulated fragments do not become Earth co-orbitals. They may strike the Moon again, collide with Earth, escape into unrelated solar orbits, or pass through the co-orbital region without remaining there. A small fraction reaches horseshoe or quasi-satellite states resembling the long-term behavior of Kamoʻoalewa. These rare outcomes show that difficult transport is possible without making the lunar origin certain or statistically common among nearby asteroids. Launch location changes the outcome because the Moon already moves around Earth. A fragment carries the motion of the lunar surface together with the additional speed supplied by the impact. Material released from the trailing hemisphere can lose part of the Moon's orbital motion relative to Earth, allowing it to escape with a solar path close to Earth's. Simulations identify this region as favorable for producing slow departures that can cross the dynamical barrier into the one-to-one resonance. Favorable does not mean common. The successful paths occupy only a narrow part of the possible launch conditions. The physical size of Kamoʻoalewa also constrains the required impact. A fragment tens of meters across must survive excavation, acceleration, and escape without being crushed into much smaller pieces. Impact calculations indicate that a crater larger than several kilometers can eject coherent blocks, but the number and survival of such blocks depend on the target rock and the violence of the event. Studies connecting size, launch speed, and orbital lifetime suggest that a relatively young crater more than about 10 kilometers wide provides a plausible source. One proposed source is Giordano Bruno, a bright-rayed crater on the far side of the Moon. It measures about 22 kilometers across and appears geologically young, with age estimates commonly spanning roughly 1 million to 10 million years. Its location lies within a lunar region that simulations identify as capable of launching fragments into Earth-like solar orbits. Its size is sufficient to produce debris comparable with Kamoʻoalewa, and its estimated age overlaps with calculated survival times for lunar fragments in near-Earth space. The identification remains a hypothesis rather than a confirmed birthplace. Crater ages derived from surface features carry uncertainty. The number of small craters superimposed on ejecta, the brightness of rays and models of impact rates all contribute to age estimates. Erosion by later impacts can blur the record. The original ejection direction of one surviving block cannot be reconstructed directly from the crater as it appears today. Other lunar craters may also satisfy part of the required size, age, and location conditions. The asteroid's present orbit does not preserve a simple line leading backward to one point on the Moon. Gravitational encounters create chaotic behavior, meaning that tiny differences in initial position eventually lead to very different calculated paths. Thermal forces add further uncertainty. Researchers contest whether lunar fragments are capable of reaching Kamoʻoalewa-like states, but they cannot reverse the current orbit across millions of years and identify one exact launch event. The connection to Giordano Bruno comes from statistical compatibility between impact physics crater properties and simulated transport. Spectral evidence gives the hypothesis another foundation. Earlier observations show reflected light, resembling strongly weathered lunar silicates. The weak absorption feature, red slope and unusual appearance compared with many near-Earth asteroids support material altered on an airless, rocky surface. Lunar soil and impact fragments experience solar wind, micrometeorites and radiation, producing coatings that can weaken mineral bands. Kamoʻoalewa's surface could carry such a history if it begins as lunar bedrock and remains exposed during its journey. A lunar fragment would not necessarily resemble every returned lunar sample. The Moon contains varied terrains, rock types, impact melts, and buried layers. A block excavated from the far side could contain material not represented well in the limited collections brought to Earth. Grain size and exposure age would also change its spectrum. A broad lunar resemblance, therefore, supports compatibility, while differences do not automatically exclude a lunar source. Observations and simulations together indicate that lunar ejecta can enter Earth's co-orbital region and that rare pathways can reproduce important parts of Kamoʻoalewa's motion. The proposed journey begins with a high-speed impact, continues through escape from the Moon, and develops through long gravitational exchanges near Earth's orbit. Giordano Bruno provides a physically plausible source, but no remote measurement proves the connection. The hypothesis remains a carefully constrained account of how a fragment of lunar crust may become a small independent asteroid carrying altered moon rock through a century of apparent companionship with Earth. The lunar fragment hypothesis offers a coherent explanation for Kamoʻoalewa, but it is not the only explanation supported by current observations. New spectral measurements and population studies allow an origin in the main asteroid belt to be considered with greater weight. The debate does not arise because one side ignores the evidence. It arises because the same faint object can be matched by several combinations of mineral composition, surface alteration, and orbital history. Each interpretation explains some measurements well, while other measurements remain difficult or uncertain. The earlier lunar interpretation depends strongly on the red slope and weak silicate absorption reported from ground-based observations. Those features resemble some mature lunar soils whose grains have been altered by solar wind and microscopic impacts. Kamoʻoalewa also follows an orbit unusually similar to Earth's, and simulations show that lunar ejecta can enter the one-to-one resonance under rare conditions. Together, surface resemblance and orbital compatibility create a persuasive case. Neither line of evidence, however, identifies the Moon uniquely. Weathered asteroid material can develop similar colors, and main belt fragments can occasionally reach Earth-like co-orbital paths. A competing explanation begins with ordinary chondritic material. Chondrites are stony meteorites containing primitive minerals formed early in solar system history. One subgroup, called LL chondrites, contains relatively little metallic iron and a low amount of total iron compared with related meteorites. Their silicate minerals resemble material measured on the asteroid Itokawa, which is a small near-Earth body visited and sampled by the Japanese Hayabusa mission. Fresh LL chondrite material does not automatically match Kamoʻoalewa, but strong surface weathering can change its spectrum. Laboratory experiments test this possibility by exposing meteorite powders to conditions that imitate repeated impacts and energetic alteration. Powdered grains respond differently from solid slabs because light passes among many surfaces and pores. Experiments indicate that strongly weathered LL chondrite powder can develop a steep red slope and a shallow absorption band similar to the earlier Kamoʻoalewa spectrum. The match suggests that the unusual redness may describe the condition of the surface rather than a lunar birthplace. A fine, mature layer on an asteroidal fragment can therefore imitate some optical properties of lunar soil. The position of the main absorption band provides another clue. Reanalysis places its center near 1 micrometer within a range consistent with minerals found in LL chondrites. Measurements of the Giordano Bruno crater region on the Moon do not provide an equally close match to the reported band center and depth in one recent comparison. This difference weakens the claim that the crater is spectrally identified as the source. It does not exclude other lunar locations because lunar composition varies, and remote measurements of crater material average many surfaces across each observed area. A main belt origin also requires a path from distant asteroid populations into Earth's neighborhood. The Flora family is one possible source. It is a large group of related asteroids in the inner main belt, probably produced when a parent body was disrupted. Many flora members have compositions associated with LL chondrites. Fragments can drift slowly through thermal forces until they reach unstable orbital regions. Planetary resonances then increase their eccentricities and carry some of them into paths that cross the orbits of terrestrial planets. One important route is the new 6 secular resonance. A secular resonance develops when the slow rotation of an asteroid's orbit becomes synchronized with a planetary pattern. Near the inner edge of the main belt, this interaction can steadily stretch an asteroid's orbit until it enters near-Earth space. Numerical simulations show that particles from the flora region and nearby resonances can occasionally evolve into Kamoʻoalewa-like orbits. The probability is low for any individual fragment, but the main belt supplies an enormous population over long periods. Population models compare the expected number of objects produced by different sources. Recent calculations indicate that the general near-Earth asteroid population can naturally contain approximately one Kamoʻoalewa-like body at a given time. The estimated contribution from ejecta, associated specifically with Giordano Bruno, is smaller in those models. This statistical result favors a main belt explanation, but it depends on uncertain asteroid sizes, impact yields, orbital lifetimes, survey efficiency, and the age of the lunar crater. Population estimates describe likelihoods across many possible bodies. They do not establish the history of one particular asteroid. New observations with the James Webb Space Telescope add another layer. Its near-infrared spectrum is much less red, from 1 to 2.5 micrometers, than the earlier ground-based measurements. Independent ground observations obtained with similar processing agree with the more neutral color. A faint absorption remains near 9/10 of 1 micrometer, while a strong band near 2 micrometers is not detected. This combination resembles several silicate asteroid classes more closely than the strongly reddened lunar comparison that first attracted attention. The thermal signal measured during these observations suggests a relatively bright surface and a body smaller than many earlier estimates. Models favor a diameter near 18 meters, although uncertainty in shape and reflectivity allows a broader range. A high albedo, neutral infrared color, and weak absorption can be compatible with enstatite-rich material containing oldamite, a calcium sulfide mineral. Enstatite-rich asteroids represent another possible comparison, distinct from both ordinary LL chondrites and typical lunar soils. This interpretation remains provisional because weak bands can be difficult to separate from calibration limits. Differences between the old and new spectra may arise from observing conditions, analysis methods, or genuine surface variation. Earth's atmosphere affects ground-based infrared measurements, while space observations avoid that disturbance. Kamoʻoalewa also rotates rapidly, so separate observations can sample different faces. If its surface contains patches with different grain sizes, weathering states, or mineral mixtures, its color may change with rotational phase. Current data do not determine whether the discrepancy reflects uneven terrain or measurement limitations. The origin, therefore, remains unresolved. Lunar ejecta explains the Earth-like orbit and preserves a physically possible route from impact to resonance. A flora family fragment explains the spectrum through weathered LL chondrite material and benefits from a large long-term source population. Enstatite-rich composition offers another spectral possibility. Observations indicate that Kamoʻoalewa is silicate-rich, rapidly rotating, and strongly altered at its surface. They do not yet identify one birthplace beyond reasonable doubt. The asteroid's faint light supports several histories, and scientific caution keeps each history separate from established fact in present scientific understanding. Tianwen-2 brings Kamoʻoalewa's investigation to direct examination of rock. The spacecraft launches in May of 2025 and reaches the asteroid in the middle of 2026. On July 2nd, it records images from about 20 kilometers away. These images reduce uncertainty in the asteroid's position and reveal a body no longer represented only by a moving point. The mission now studies its shape, rotation, surface materials, and internal structure before attempting to collect a sample. Close imaging can measure the outline. Repeated views from different angles allow researchers to build a three-dimensional shape model. Shadows reveal ridges, hollows, blocks, and loose deposits. Changes between images show the rotation state and the orientation of the spin axis. The distribution of craters can indicate how long parts of the surface remain exposed, although weak gravity may modify familiar crater forms. Imaging also identifies regions smooth, stable, and well illuminated enough for sampling. Spectrometers aboard the spacecraft separate reflected and emitted radiation into wavelengths. Their measurements can determine whether the weak, silicate features seen from Earth occur across the whole body, or only on selected areas. They can compare brighter patches with darker terrain and distinguish fresh exposures from strongly weathered grains. Thermal measurements follow how quickly the surface warms and cools, providing estimates of grain size, porosity, and thermal inertia. Together, these observations connect remote spectra with locations on the asteroid. Radar and gravity measurements can examine structure beneath the visible surface. Radio waves may reflect differently from solid rock, fractured blocks, and porous mixtures. The spacecraft's motion around the asteroid responds to its weak gravitational field, allowing the total mass to be estimated. When mass is combined with the volume from the shape model, researchers obtain bulk density. A density close to solid silicate rock would support a coherent fragment. A much lower density would indicate large empty spaces, extensive fracturing, or a rubble-like interior assembled from separate pieces. Sampling such a small and rapidly rotating body requires careful control. Kamoʻoalewa has almost no gravitational pull, so a spacecraft cannot rest on it as easily as a lander rests on the moon. Contact can push both the probe and loose material away. Tianwen-2 is designed to use more than one sampling approach, including collection, while hovering brief surface contact and attachment to the body. The final method depends on the terrain rotation particle behavior and mechanical strength revealed during close observation. A collected sample may contain dust chips, glass mineral fragments, and material altered by solar wind. Even a modest quantity can answer questions that remote light cannot settle. Cameras and spectrometers measure averaged surfaces, while laboratory instruments examine individual grains. Scientists can cut particles into thin sections, polish exposed faces, and study them with optical and electron microscopes. Crystal shapes, fractures, impact melt, and tiny coatings become visible at scales ranging from millimeters to fractions of a micrometer. Mineral analysis can determine the proportions and chemistry of olivine pyroxene, enstatite, feldspar, sulfides, metals, and glass. The amount of iron within silicate crystals shifts spectral absorption bands and helps distinguish lunar rocks from several meteorite groups. Enstatite-rich material would support comparisons with certain bright asteroids. Mineral mixtures resembling LL chondrites would strengthen a main belt interpretation. Lunar minerals impact glass, and weathered coatings could support ejection from the Moon, especially if their chemical relationships match known lunar crustal material. Isotopes provide a deeper test. Isotopes are forms of the same element with different numbers of neutrons. Oxygen isotopes are especially useful because planetary bodies often preserve characteristic ratios established during formation and later processing. Lunar and terrestrial rocks share very similar oxygen isotope patterns, while many asteroid groups differ. Other isotope systems can reveal heating, melting crystallization, and the age of mineral formation. No single ratio determines origin alone, but several independent systems can create a strong chemical identity. Microscopic grains can also preserve evidence of exposure to space. Solar wind particles become implanted in their outer layers. Cosmic rays create rare isotopes deeper within the material. Measuring these products can estimate how long the rock travels as an exposed body and how long individual grains remain near the surface. A short exposure age could support relatively recent ejection from a larger parent. A longer and more complicated history could indicate residence in the asteroid belt before entry into near-Earth space. Impact features inside the sample may reveal its parent environment. Lunar ejecta can contain glass produced by impacts into dry crust fragments welded from several rock types, and mineral damage created by extreme shock. Main belt collision fragments can contain their own shock veins, breccias, and melted zones. The textures overlap, so interpretation requires comparison with returned lunar material. Meteorites, asteroid samples, and laboratory impact experiments. Context from the sampled site remains essential because one grain may record an event unrepresentative of the entire body. The condition of organic compounds and volatile elements may provide additional information, although a silicate-rich surface near the Sun is unlikely to preserve abundant fragile material. Careful handling protects the sample from Earth's atmosphere, moisture, dust, and biological contamination. Sealed containers allow laboratories to measure gases released from minerals and examine compounds present in very small amounts. Portions can be stored for future instruments whose sensitivity and methods do not yet exist. A returned sample would not merely assign Kamoʻoalewa a familiar label, it would connect orbital dynamics, impact physics, surface weathering, and mineral history within the same measured material. Chemical signatures could show whether the asteroid leaves the Moon, escapes from the main belt, or belongs to another rocky population. Exposure ages could constrain when it becomes a separate body. Grain coatings could explain why its spectrum changes between observations. Internal textures could